So, this is the seating chart. Now, the seating chart goes with me up at the front, right? When you're looking at it, though, it's going to go like this. You have to turn it around, find yourself, but you don't want your name upside down when I'm looking at it. So you find yourself, you orient the paper, you find yourself, then you turn it around and write your name.
As if you're looking at the top.
Yes, you want it oriented like this, but then you have to turn it around to write your name so that your name is the same as my name. Okay? Got it? Okay. Pass that around. And then we have to go through this homework. Now this one, as I said, may be a little bit tricky, but you actually have all the tools to figure it out. Yes, they're different. But get there. Okay, so here I have a diagram. I have the clouds embedded in the atmosphere. I say that the optical depth of the atmosphere in the red is 0.04. Does that include the clouds? No, it does not include the clouds. So what do you do with the cloud optical depth? You have to figure it out somehow. And how are we going to figure that out? We have information here that will let us figure out optical depth.
You find those first.
Yeah, we have this. So we can go ahead and we're going to do Spear's law. Now, what I'm going to do to keep it easier is we do one wavelength at a time. So if I'm writing in red, I'm dealing with the red wavelength. Okay? So, we can say with Spear's law that I over I0 is equal to e to the minus tau. There would be a cosine theta, but we're not going to worry about that now, right? Okay? And then, of course, you can solve that for tau. So we're going to get that tau is going to be equal to negative logarithm of I over I0.
Good.
And when you do that, what do we get for our optical depth?
19. Optical depth.
Optical depth.
0.32.
What?
0.36 for the total or for the?
0.3166.
Point for the total optical depth.
0.36.
0.36. Okay, that is our tau. However, is that the tau of the atmosphere? Is it the tau of the cloud? Or what is it?
It's the multiple effect.
And how, when you say multiple effects, how do we deal with that mathematically?
So you have to take your tau totals and subtract the tau of the atmosphere.
Okay, so I'm going to write tau atmosphere plus tau of the cloud. Right? And make everybody happy?
Wait.
Because this beam of light is going through the atmosphere and through the cloud.
So it's the
So-
sum of the time.
Yeah, so this optical depth that we calculate from those two numbers comes from the combined atmosphere and the cloud.
Yeah.
And because an optical depth is the amount of stuff, you're adding it together. Okay? So yeah, we could call that like tau total there. So in that case, we get that tau of the cloud in the red light is equal to tau total minus tau of the atmosphere. Okay, so 0.36 minus 0.04 is equal to 0. Now there's some rounding going on here. So, remember, you may get different numbers depending on your rounding. In fact, when I was doing it very carefully, I ended up with 1983 at the end of this. Okay, so this is the optical depth of the cloud in the red light. Okay? So now we go over here and say, okay, we have this initial intensity. We want to find the final intensity. What do we need in order to get that final intensity? We need the optical depth. And we need the optical depth of two things, right? The atmosphere and the cloud. How could we get the optical depth of the atmosphere?
by using the formula lambda over lambda.
Yes. We know it's going to be Rayleigh scattering. It's a really tiny molecule with visible light is in the micron range or so. So we can write something like this. I guess I'll do tau. I'll write green there just to remind people over tau red. And this has to be in the atmosphere. Anyway, let me just write. I'm just going to write because we have the colors. Atmosphere, tau, atmosphere. This atmosphere, tau in the green and in the red. That's going to be equal to, and then we have to be careful. We have to invert this. Lambda over lambda to the fourth power. Okay? I think that most of you will at least figure out to do this.
Yeah.
Okay? And you know that this, which tau are we using here? Are we using 0.36? Which one are we using? 0.04. Yes. So if I rewrite this, tau atmosphere in the green is equal to tau atmosphere in the red. Yep. Lambda over lambda. The fourth power. And then if we start putting in our numbers, now it needs to boil to black. We can say it's going to be equal to 0.04 times lambda in the red.
Yeah, 0.7.
Yeah. Oh, yeah, either 0.7 or 700. We can do either way. Like that's microns over 0.4 micron. Oh, 0.5. Thank you. Green, not. I was thinking blue there. 0.5. And work that out. And what do we get for that? 0.15. 1.5. That seems not
0.1539.
153. Okay. 154, something like that. Okay, so now we have the optical depth for the atmosphere. But that's not enough, is it? Because we need the optical depth for the clouds. How are we going to get the optical depth for the cloud? We know the optical depth for the cloud in the red. How do we get it in the green? Can we use Rayleigh scattering? This 20 micron sized particles. These are big compared to the wave. What kind of scattering is it? Geometrical. How does geometrical scattering change with the ratio of size to wave? It doesn't.
They're 1-to-1.
It's the same optical depth. Because however much red light I intercept the same fraction of green light. It just goes geometrically as the area, and the area hasn't changed as I go from red to green.
So it's equal.
So it's the same optical depth. Okay, so I can write in the green, I can write T total is going to be equal to T of the atmosphere plus tau of the clouds 0.154 plus what did we have up here?
0.32.
Yeah, 0.32, so 0.474, something, 472. Okay? No, 474, yeah, 474. Okay? That's the total optical depth in the green. And from there, I think you know how you could do it, right? Okay? So there's a little trick of realizing, oh, geometrical, everything's going to stay the same.
So in the atmosphere, it's Rayleigh, but in the cloud, it's
In the cloud, because you have a very large particle compared to the wavelength, it's going to act the way you expect things to act. It's going to absorb this red and green light the same fraction, or reflect, I should say.
example is like kind of the cloud.
Yeah.
So the optical depth for the green light is the same as the.
Yes.
Why
The way to think about it, optical depth is how much light is being intercepted. You know, whether it's absorbed or scattered, something like that. You know it's only being scattered. So how much light is being scattered? And because these particles are so much larger than the wavelength, they scatter the same fraction of red and green lights. The wavelength doesn't matter anymore. So it's going to be the same. Okay? So from there, the boom, 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 you work it out, right? I don't have any more. I guess I can get rid of my diagram. So we can say, oh, we're going to be in the green now. So I is equal to I0 e to the minus tau 3,000 watts per meter squared per micron. By the way, why am I being so careful to make sure I write micron down there all the time?
Because
We're changing wavelengths, so we have to remember this is what's going on around this little wavelength. And as far as the units go, it's not going to matter. There's not going to be any canceling out and stuff like that. But it just reminds me, oh, we're dealing with specific wavelengths. So I have to have the micron in there to remind me this is around a certain wavelength. So e to the minus 474 with a big point in front of it. And then you do it. I don't think you come up with 1880 exactly. You come up with something a little bit different.
1860.
Okay.
Wait, I thought.
And so it comes out with how much rounding you've done.
But I,
Yeah.
I found the same result when it was a different method.
What was their different method? How did he get the optical depth of the cloud?
I added, I found it
Yes.
and I found it 15, and I found it in the second somehow in the middle. But then on the paper it says 1880. That's why I didn't use this result.
Okay.
So I added it.
When you're dealing with exponentially or rounding, you're going to get numbers that will change a lot. Anyway, that is the correct way to do that. Okay? Yes.
So just to get this in perspective, right?
Yeah.
The parts was 20 microns,
Yes.
right? And then the intensity going to the part changes to, let's say, whatever. So we need to optical depth for both the atmosphere of solar and the cloud.
Yes.
So we need the total.
Yes.
That's why we're getting.
Yeah. And the optical depth of the atmosphere will change from red to green, but the optical depth of the cloud will not change. The atmosphere is a little tiny part, whereas the cloud is a big part.
Okay, so for the cloud, it won't change.
It won't change. Yes. Okay. Yes.
If the particle size of the clouds were much smaller, Rayleigh scattering, it would be.
Yeah, but it had to be much smaller than the wavelength of the light. It doesn't really happen with clouds. Aerosols, they actually get close to the wavelength of light, and they actually do Lee scattering, which gets really complicated. Yes.
So I have a question. So I did one, I don't know, I couldn't really hear what she said. I don't know if it's the same way I did it, but so what I did was I calculated the intensities of the red and green after the atmosphere for the clouds.
Okay.
And then I used that equation after calculating the relevant optical
Yeah.
depths. I used the equation where the transmitted intensity over the original is equal to 1 over 1 plus the optical depth.
Okay, so you're using the scattering equation, but you don't know the backscattering.
Right.
That's where you need a problem. For
Yeah.
droplets of water, backscatter is 15.2. But you wouldn't know that.
Yeah.
But that's why I was saying, you know, let's go ahead and use the Beer's law, even though technically it's not quite correct.
Yeah, I found it interesting that when I solved that, I just said that
You got about to say, you got it right. What did he do about the cloud optical?
so what I saw was that the backscatter times the optical depth would be for the cloud, and then I realized if I used that same value and plugged in values for blue,
Okay, so you're ending up with the
Green.
same, you actually use the same optical depth for the cloud and the green.
yeah,
Yeah, you did the same thing. You just used the correct multiple scattering equation rather than Beer's law. And it's going to be a little bit, because these optical depths are pretty small, they're going to come out about the same.
oh, okay.
Once you come up to bigger optical depths, then you're going to see the divergence between Beer's law and the 1 over 1 plus b.
Okay.
So, yeah, 55. Okay. So, the other thing. So, yes.
So, in terms of like looking at sizes and making like a decision on whether it's Rayleigh or E
Yeah.
or geometrical, like what's the what should be like the factor?
Roughly a factor of 10.
So no more than, if it's more than a factor of 10, then.
And then, yeah, but about 10 times bigger or smaller, if the wavelength is 10 times bigger or smaller, or the particle is 10 times bigger or smaller than the wavelength, that's when you kind of decide you're switching to another regime. But it's rough.
Yeah, because that
I
one
mean,
is like.
you know, around the factor of 10, you're going to be some re-scattering going on. and
Okay.
You're going to have like, it's going to be the ratio of the wavelengths to the power of 3.5 or something like that. Kind of approaches the rate.
Yeah, because if it's me scattering it, makes it really like complicated.
There's something called an angstrom exponent where that exponent here doesn't have to be 4 as you become closer to the size of the particle. It begins to drop down towards 1 and even 0. That's used as a way to estimate the size of the particle. In fact, you're going to be doing that tomorrow.
Okay.
Yes? Okay. Yeah, I know you guys kind of want to work down for your own edification too. Hang on to the homework for a little bit. Okay, now we move into our last new conceptual material here. We're talking about thermal radiation. As we had talked about absorption, we talked about scattering, now we have to talk about emission. And we're all busy emitting right now, there's nothing we can do about it, so may as well understand it. So, we talk a lot about what's called black bodies. And here's the concept of a black body. This was physicists around 1870, 1880, you know, they were trying to figure out what happens if we have light that goes into a cavity. And that's going to bounce around a lot, and it's going to, you know, affect the temperature, and after bouncing around, it's definitely going to be absorbed. Because you only have a little hole here, so it's going to be absorbed. But you're also going to get radiation coming out of the mouth of the cavity. And their logic here was a cavity that any light that goes in will definitely be absorbed. It's going to behave the same way as a perfectly absorbing body, which is called a black body. Okay, so this is called black body radiation. What happens if you have something that absorbs perfectly? By this argument, I could make this out of wood, I could make this out of metal, I could make this out of anything. It's going to radiate the same amount. It's going to behave the same way. So the idea is every perfectly absorbing body behaves the same way. It's going to radiate the same way. If we can figure out what's going on here, then you know what's going on with thermal emission. Okay? And it turns out as they tried to work this out, they weren't having any luck getting it to work out. So the guy who finally figured it out was called Max Planck. This is where Planck's constant comes from. We could take a whole lecture deriving the black body from, it was the beginning of quantum mechanics. Nobody knew it at the time, but it was the beginning of quantum mechanics. So, we're not going to derive it, we're just going to tell you what the final result is eventually. But you're going to see these little H's, you're going to see C's, and all of this modern physics stuff is going to come creeping into that equation. But let's just say we're talking about things that are perfectly absorbing. Which things will act like thermal black bodies? Well, it turns out that water absorbs infrared radiation very well. So if you have a cloud that's thick enough, it would behave and radiate like a black body. It would behave like a perfect absorber in the infrared, not the visible, but at least in the infrared. Now, of course, you know the very edges of a cloud that's not absorbing everything. You actually have to get at least one optical depth in there. And if you're looking at the temperature of a cloud and the radiation, it's kind of like it's coming from deeper inside the cloud, is what we see. Okay? Now, what else? Land and water, these things will also absorb very efficiently, so they're going to emit fairly efficiently. Now, some materials are not going to have 100% emission efficiency. We're going to come back to that. Most things are around maybe 95% perfect absorption efficiency. So they're going to emit kind of like that. But, so if you're looking at water or if you're looking at ground, you're looking at usually a few millimeters into the surface. That's the temperature that you're looking at. Now, one thing that's very important here is if I have an object inside the cavity, this case here is at one temperature and the object's at the same temperature, they are in equilibrium. So the surroundings are radiating at that object. If it's staying at the same temperature, what can we say about the outgoing radiation?
The same.
It has to be the same to be in equilibrium, okay? So that means that at least at equilibrium, this object absorbs as efficiently as it emits. Which means that the absorption and the emission coefficients must be the same because they're at the same temperature. Everything's at the same temperature. So, in equilibrium, absorption must equal emission. So this means that the absorption and emission coefficients must be equal. And then we take one more step. If we happen not to be in equilibrium, it's not absorbing and emitting the same amount because it's not in equilibrium. Maybe this thing is hotter or colder. But do you think the absorption and emission properties have changed? Just because it changed the temperature of the object. It may be emitting more, but is the basic ability to absorb and emit, is that going to change? Actually, it's the same material. It has the same capability of absorption and emission. Just because you change the temperature a little bit doesn't affect that. Now, if you change it enough that it begins to melt, there's an ice cube in the melt, then it's a different material. But so long as the only thing that you're changing is the temperature, it will absorb and emit at the same efficiency. Because it has to, otherwise it can't even reach equilibrium. Okay? So
even if they're different temperatures, they have to reach equilibrium at all times.
they have to have the capability of reaching equilibrium, which means that they have to absorb and emit the same efficiency. That doesn't mean they're absorbing and emitting the same amount. Because maybe I'm absorbing more, but I'm absorbing 95% of what hits me. I'm going to emit at 95% of my potential emission. Okay? 95% as efficiently as a perfect absorber. So, the question is, what does this spectrum of emission and absorption look like? if you heat up something, it's not just emitting white light, it will be emitting different colors. And it's going to be emitting across a whole spectrum. We want to know what that spectrum looks like. So, one thing that we're going to do, and you guys are going to have to be careful, your oil ducts here. We're going to be lighting some candles here. We're going to be looking at the candles. For those of you who maybe don't trust yourself so much, you want to take these candles and then we're going to convert the candles. It'll be like one for every 2 people here. But we're going to light them up for people. Now we have to get lucky because I've ended up down only 2 matches here. See what my skill is. I will after we light them. Light that guy. I'll pass it around, 1 per table, and some people are going to have the birthday candles. Stay away from the paper.
You know that actually, there's people that work in. No, those places where you create like metal pieces
Okay. Oh, you got one? You got one?
Oh, yeah.
Okay. I think we got everybody covered here. Now, I'm going to turn off the lights here. And first thing is, where is the flame going to be hottest?
At the very center.
Near the wick, okay? What color do you see near the wick? Blue, okay? Blue is corresponding to the hottest color. What happens if you go further away?
Red.
It's going to turn into red. Now, these pictures don't really come out right. It seems to work better with the flames. This is why I gave you the flames. Okay? So blue is the hottest, red is the coolest. What do you see right next to the wick? Do you see an empty space? Yeah. What is that?
Is there radiation? No, I don't.
Well, actually, this is a black body here. What do you think it just cool suddenly right near the wick? No, it's hotter near the wick. So why don't you see anything? Beyond the blue, is there any light?
No, it's just,
There is electromagnetic radiation. Go past the blue, past the violet, ultraviolet. There's actually ultraviolet light coming from right near the wick. Beyond the red, it looks like the flame stops, but do you think the flame really stops?
Oh, so we're not,
Oh,
just can't see it.
infrared.
Infrared is going out beyond the flame. Our eyes just can't see it. Okay?
Interesting.
Yes.
So we're putting this in like a sensor that can see UV and
Yes.
you can see it then.
If we had an infrared camera out here, you'd see a great big flame. Well, the way up. And if you see the ultraviolet, you'd see your colors there. Okay? So, the colors go with the temperatures through the spectrum. And we're going to be talking about where that comes from. So now what I want you to do is stave off any possible incident here. Blow out your candles. I want to make sure I get the birthday candles first. All the other candles, collect these things back. Yeah, go ahead and collect them. Okay. So, if we make a graph, it turns out if you're seeing blue, do you think that completely pure blue you're looking at? No. It's actually the blue is a predominant color, but there's other colors. What's going on would be something like this. Now, I'm doing it in frequency and I'm using these colors up here. If we have something at a particular temperature, and right now I'm using terrestrial temperatures here, you'd get a whole bunch of different frequencies, which means a whole bunch of different wavelengths. But there is going to be a peak at a given wavelength. And here I'm going from 270K, which is right up about freezing, up to about a little above normal room temperature. We can see that that peak is shifting, and shifting to higher frequencies. Higher frequencies, higher energy. What happens to the wavelength as you go to higher frequencies? Getting shorter. So blue is shorter wavelength, higher frequency, higher energy. You're going to be getting a peak in the blue at that color that you're looking at. Okay? Now these are not the temperatures that are going to give the colors that you see. These are more like Earth-like temperatures. But if I had shifted these around, you'd be getting different colors depending. And they're, like I said, they're not pure colors. They're surrounded by all of these other wavelengths, all of these other frequencies as well. But there are peaks. Now, the neat thing about this is it turns out that the location of the peaks change in a linear fashion with the temperature. And the reason I'm plotting this in terms of frequencies, because frequency is directly proportional to the energy. So the energy of the peaks go directly with the temperature. Okay, which kind of makes sense. Now, by the way, I was talking about all these guys who were trying to figure out what this curve would look like. What they were calculating, and they were doing standing waves and cavities and stuff like that, they had that the energy just kept shooting off to the infinity. And they couldn't come up with any calculation that as you went to higher energies, you didn't get more and more energy being emitted. It was kind of ultraviolet catastrophe. And the way that Planck solved it is he said, well, let's say it comes in chunks. And then it takes, before you can fill up a big chunk, and the big chunk flies away, a bunch of the smaller chunks will take the energy away. So you end up that it dies away as you go to higher energy. That's kind of the way it works out. But it was a quantum theory, and it took them about 15, 20 years to figure out that they had started something new here. Okay, so there's a couple of useful formulas here. I was saying that temperature goes proportional to wavelength, and then if we do energy, frequency, if we move the frequency over, changing the wavelength, we get this formula. The temperature times the wavelength at the maximum is going to be equal to a constant. So as the temperature goes up, what does the wavelength at the peak do? It decreases as it stays constant. That's Wien's displacement. They had figured this out experimentally, but they couldn't explain it from theory. And then the other thing that we have is if you want to look at the total amount of energy being emitted, which means you have to integrate up all through the frequencies or wavelengths to get the total energy, that ends up going as temperature to the 4th power. Now, by the way, am I going to measure that temperature in Celsius?
Kelvin.
Kelvin. It has to be Kelvin because it has to go to zero emission at 0 Kelvin. Okay? And then you have a universal constant there, which is made up of H's and C's and stuff like that. So, unfortunately, this thing, the sharing thing, comes about 5.67 times 10 to the 8 watts per meter squared per Kelvin to the 4th. So you can figure out how much energy is being emitted. By the way, you've all heard about climate change and stuff like that?
Yes.
This is a big formula for calculating the temperature of the Earth. In a different class, we would calculate the temperature of the Earth and what greenhouse gases are doing, but we don't have time to do that now. Just know this is where it comes from. So, let's do a little calculation here. So we have the Earth's surface temperature in the summer is about 300 Kelvin. The Earth can be treated approximately a black box, typical, thermal IR. So at what wavelength would peak emission occur? This one I don't think I need to help with. You can work this one out. So we're talking about 300 Kelvin. What is the wavelength of peak emission? And I can begin erasing this. Some constant. Oops, wrong way. 2 When you do that calculation, what do you get? 9.9 something. 9.6? Okay. 966 microns. So the Earth at typical temperatures is radiating, the peak radiation occurs around 10 microns or so. Remember when we were talking about infrared, I said the number to remember is about 10 microns. Okay. What is the number of watts emitted from 1 square meter of surface? So now we're looking for the total power. We're going to be using the other equation. I'm going to call this power is equal to m of b k to the 4th. And then that's, what is it? 5.67 times 10 to what was it, negative 11. Per calculation 4. 3, let's write this. 3 times 10 to the second Kelvin. 5.67 times 3 to the 4th times 10 to the, what power am I going to have? Right, yeah, here we have 8. Wait, is that 11? Is that correct?
Yeah.
That was correct.
-8.
Okay, so we're going to have 8 minus 11, so we're going to get minus 3. Wait.
No, minus
No,
8.
that's minus 8.
Minus 8.
Thank you. I knew that wasn't coming out right. So, the first. Yeah. No, do the 0.
Oh, yeah, because yeah.
Yeah, and then it's going to end up with being watts. So that you just have to work out what that thing is. So 5.67 times 81,
459.
459 watts, which is about 4 watt in every square meter, the equivalent of like 400 watt bottles. So it's actually quite a bit of energy. That's kind of surprising, isn't it? So yeah, it is as though you're being radiated from every square meter. It's like 4 watt light bulbs are radiating infrared at you. And which is a good thing, because if that weren't happening, we would freeze. So it's keeping us warm. Because space is really cold. Okay? So far so good for this.
And then the surface area, you would just divide it by, for that 100 watt.
Oh, and this is for 1 square meter.
Yeah. And
So
then it
because we ordered, this is, sorry, yeah, that's 50 watts per square meter. So if you want to get how much the total energy is, you multiply by the area. So that should be or so meters squared down there. Yeah.
How much surface area would emit like 100 watt?
Well, if 1 square meter of the Earth is emitting 459 watts per square meter, it's about 4.5 watt light bulbs. But maybe that's for red. Yeah, just divide by 100.
What do you mean by watt bulb?
Oh, maybe you're not familiar with this terminology. It's not so common now that we have this fluorescent lights and so on. But you usually go to a hardware store to buy a 60 watt bulb, buy a 100 watt bulb. People don't really talk that way anymore. I should probably change this thing so you don't see incandescent bulbs anymore.
Is it a unit or just like a
Watts. Watts, 100 watt bulb. I need to change this for the current generation. Yes.
So I was just curious, so that equation, so the left hand side will be the power over meter squared? Or
Yes, it's power per meter squared, power per area. So, yeah, I should say power per area is really the better way to write that. Okay. So far, so good. So, those were just aggregates of the equation. Let's look at the actual shape of the equation. Now, when we talk about this, we have to be a little bit careful because we're talking about the energy emitted across a wave of a range of wavelengths. If I know that intensity is some power, I'm talking about intensity across what range of wavelengths. So if you integrate from one wavelength to another wavelength, the reason I'm integrating is because the amount of power emitted will change with the wavelength. But then there's this function. This function depends on the wavelength of the temperature, and I'm integrating over the wavelength. Or I could do integrating over frequency. Now it turns out the function of frequency is different from the function of wavelength. I really should write a slightly different b over here than I have over there, because they're not really the same function. So, in the wavelengths, we end up with this equation that exp means raised to the exponent of, but we do that so you can see these, otherwise it's too small to see. Okay? The e to the hc over lambda kt. Like I said, h and c, you see the modern physics creeping in there. K is actually Boltzmann's constant if you've done the chemical thermodynamics work. And you would think, oh, if this is wavelength, I can just substitute wavelength with c over f, right? I should be able to do that. However, you can't really because we have d wavelength and we have d frequency, and those have to be part of it. So I have to make this conversion. Df is d wavelength over c lambda squared. So here I have frequency to the third. Here I have wavelength to the fifth because of the df and d lambda type conversion. Okay. Now I prefer to work in wavelengths, so this is going to be that equation that we're going to be using to give us the shape of intensity as a function of wavelength.
The exp is e to the, right?
E to the, yes. But if I wrote that, you'd be squinting trying to see it. Yes? Yes.
So in this case, instead of velocity, we use 3 or 9.
Say that again?
Instead of velocity, we use 3.
Yes, C is the speed of light.
Okay.
Yeah.
I mean, in this case.
Yes. I guess you're probably asking if I use the speed of light in air or in a vacuum. It's for a vacuum. Okay, even though we're in air or even in water, it's what is the same speed. Okay. And then we have all of these units here, which is getting a little bit nasty. So let's gather up constants. So we're going to gather up all of these things and multiply them out. We're going to call that A. Gather up all of these things. We're going to call that B. And I didn't put the units in here, but you have to know that you're going to be dealing with microns and areas in meters and power in watts and stuff like that. Okay? So now we have a little bit of an easier equation to work with down here. However, when you do this, you're going to find that since everything is in meters, you're going to come up with an answer that comes out in watts per meters cubed, not watts per meter squared per micron. So then you want to convert one of these meters into microns at the end. Okay? So we've got a new kind of nasty equation. I think we should use it. But before we get there, we have to talk a little bit about how we use it, because the integrals are kind of funny here. Now, for one thing, we're often going to be talking about non-ideal objects, things that don't absorb perfectly and don't emit perfectly. So we have to throw in a new constant, this emissivity. So we're going to be we just multiply it with like absorbs 90% of the emission, this emissivity is 0.9. So, okay? So this would be our equation, how much energy is being emitted between two wavelengths. If you look at one specific wavelength, and say, okay, I'm just looking at what's happening around that one wavelength, we will often kind of throw away the integration and we'll just go like this. It's not quite right because, yeah, it is going to change with wavelengths, but if we stay close to one wavelength, we can kind of get away with it. So this is mainly what we're going to be using. So let's go ahead and try it. Before we do this, by the way, notice that emission is going to be equal to absorption. So sometimes we're going to be switching between emission and absorption because they should be the same constant, what we talked about. So we have this concept called brightness temperature. If you're working with remote sensing, you're going to hear the term brightness temperature over and over and over again. And what it means is, what if I observe a certain radiance coming up on a wavelength, what temperature would be necessary to produce that radiance that I'm observing? And that's called the brightness temperature. So temperature is equal to B, and then you're going to have to solve that equation for the temperature in order to get the brightness temperature.
So you would have to know the intensity?
If you measure the intensity, you go to the equation, you solve it for temperature, and then you get the temperature at a given wavelength. So the intensity at a given wavelength. Okay? However, you have to remember, maybe some of this is being absorbed by the air. If you're out of a satellite, some of this radiance may be absorbed, so you may not get the right temperature. You may not know the emissivity of this object. You may be assuming the emissivity of 1, but really emissivity of 0.92 or something like that. All of these assumptions will change the temperature that you calculate. But this is why when we're getting temperature from a satellite, don't say we're measuring the temperature from the satellite. We are retrieving a temperature because we're making assumptions. And there may be varying qualities of assumptions, but we're usually making some assumptions when we get the temperature. So all of this is probably spinning around in your head until we do a calculation. Okay? So, we have some stone. We're going to find out later that if you have nicely polished marble and stuff, it actually doesn't emit very well. If you've ever walked by a marble monument and you've got nice polished marble monument, it's kind of cool. it doesn't emit as efficiently as other things do. So we have some strong emissivity of 0.7 at a wavelength of 10 microns. What is the spectral intensity of thermal radiation at this wavelength if the surface temperature is 300 Kelvin? Okay, so we have a wavelength, we have a temperature, we have an emissivity. So we can go ahead and we can start plugging it in. Now we're doing it at a specific wavelength, so we don't have to integrate. In fact, I'm not going to make you integrate these things because that's no fun to integrate. So we say intensity in watts per meter squared really should be per micron here. Figurating, whatever. Okay. As an equal to emissivity times its function times the wavelength. We're going to be using a delta wavelength, or let's say per micron. So we're going to set that equal to 1. Okay? And remember, we're going to say per micron. So we're going to set that delta wavelength to 1. So we have to convert everything into meters first. So our wavelength we have to convert into meters. And then we're going to substitute. So here's our equation. I'm going my 0.7 for the emissivity. A is that number that I had given you. Wavelength, we have 10 microns. I converted that into meters. The microns 10 to the minus 6, 10 microns 10 to the minus 5 to the 5th power. Exponent of this constant. There's our wavelength that can convert it to meters. There's the temperature, minus 1. Okay? Now, how many of you would plug in all of these numbers straight into your calculator just the way to read it? Dangerous. What should you do?
Find each individual one.
Getting there. First of all, you need to clear out the powers of 10. Okay? Always work out the powers of 10 before you stick to your calculator. Why? Because these powers of 10 is 1, 2, there's like 4 symbols I have to type in. You can make a mistake. You're doing this over and over. However, it's nearly impossible to mess up calculating powers of 10. So always do that first. Simplify as much as you can before you plug into your calculator. So I would simplify this. So we're going to have 0.7. Actually, all of the one things you get. 0.7 times 1.19 times 10 to the minus 16. That's fine. Then we're going to have watts per meter squared. And though in the past I haven't been careful putting in units because I knew they were going to cancel out, here you want to be more careful. Make sure you put in one of the units and make sure they cancel out. So 10 to the minus 5 raised to the 5th power, 10 to the minus 25 meters to the 5th, times, now we're going to have my exponent there. So what's going to be my final power of 10 with all these exponents? 10, so we're going to end up with 10 to the minus 3, come up there 10 to the 1st division, right? And then 1.441 over 3.
Isn't it 10 to the negative 1? Oh wait, no.
10 to the negative 3 comes up there 10 to the positive. Okay. Let go of my units. This cancels out, that cancels out. Oh, well, the units cancel out. By the way, if the units don't cancel out, and I'm doing an exponential, I'm doing something wrong. You know, whether the units in an exponential or in a cosine, or all of those units have to cancel out. So if they didn't cancel out, you've got a problem. And then I can subtract 1. Okay? So this is a little bit, oh, by the way, we have all of these powers of 10. And those powers, so 10, 16, 10 to the 25, what would that become? 10 to the 9th. Here's the 5th, here's up there. So that's going to become 1 centimeters cubed. something didn't go quite right. No, what? Per meter cubed. Okay. And that's something you can now stick in your calculator. Okay? Much safer than doing all of the powers of 10. Do the powers of 10 yourself. Don't waste your calculator doing powers of 10. Yeah. Yeah, this is a constant, that's a constant. Okay. That was the A and the B from B. Okay, so you put that in your calculator, you're going to get 6.89 times 10 to the 9th watts per meter cubed. And then we can take one of those meters cubed and convert it into microns. Okay? Is it 10 to the 6? Yeah. So we convert one of those meters cubed into microns, the 10 to the 6 goes away. Okay, 6.89 watts per meter squared per micron. And then your final answer. Okay? So you see all the little games I had to say to make that work out. So, now that I've done that one for you, I'm going to give you the harder one. We're going to go in the opposite direction. The vegetation has an emissivity of 0.9 at 10 microns. A satellite measured a spectral intensity of 7 watts per meter squared per micron. Looking at a vegetative picture, what is the brightness temperature? So what you have to do is you have to take the equation that we had before, but this time solve it for temperature. Now, before you start doing this, how many of you are going to substitute in numbers first and then solve? Don't do that. Solve algebraically. I know it's a pain, but the reason you want to do this is you're going to find out all of these numbers, sticking all of these numbers. You're the pain in the butt, wasn't it? Wouldn't you rather write a computer program where you just put in wavelength and stuff like this, and boom, and magically pops out the answer? That's what you need to do. In fact, we're doing MATLAB, so you can write MATLAB. So what you want to do is you want to write that algebraic equation, invert the algebraic equation, and then you can write a MATLAB program to go and do all of this for you magically. Just pop in the numbers and boom, you get the answer. Okay? So, right now I'm going to make you sweat through the algebra. Now, do you need me to go back and, well, okay, I'll leave that too. But remember, what we have is intensity is equal to E times A over wavelength to the 5th. Wavelength to the 5th times E to the minus D over lambda T minus 1. So we can solve that for a temperature. Oh wait, do I have that right? I think I have the wavelength in the wrong place. Yeah, no, it's right. Question?
Why did you make it minus b?
Yeah.
Oh, because I'm wrong. Because I'm not used to writing exponential to the negative, and jumping there, I forget, oh, it's not a negative. Okay. Let's stop for a moment first. What's the algebraic equation that we get for temperature? EB. What?
V over
Let's not look at one thing. Keep going.
V over lambda lambda
Yeah, it's V over. Exactly. That's it. Yeah.
Oh, it's
No,
different.
that's, yeah.
That thing there.
Normally that's it.
And then
Negative
plus
one.
one.
Negative one. Before you close.
Before it says, yeah. Now what people got? Wait, do I have two E's?
I got
That's not what I get though.
And the left is like.
Plus one.
It should be outside.
Plus one.
Plus one should be outside.
It's not. I thought it's not.
Plus one should be outside.
Because you have to put the LM for everything.
Yes.
The LM has to be for everything.
Like that is. Plus one is not.
No, it has.
No.
Yeah, that's
not
like
lambda.
pretty- That's what.
You can write it down again,
I-
because you have to put LM.
Oh, okay.
Because the exponent.
I got,
Okay, okay, okay.
No, but it's
okay.
Oh, it's not even that.
Is that not right yet? We could work it out, and now you know.
Yeah, that's what I get.
That's what you get.
No, this, the minus one is
That what you
It's
got?
because we wrote the
Yeah.
exponent.
That's what I get.
Yeah, minus one is not exponent, yeah.
We okay? Now, when you plug in, what's one thing that you need to convert? Lambda has to turn from microns into meters when you do the calculation, then you can turn one of them back again. So actually, I don't think you need to turn any of them back. Just plug it in. So, have you plugged everything in? Or are you still working?
Plug everything in.
Okay.
I got that.
Yeah.
76.
76, something's not right there.
So these 100 and the wavelength is 10. So
Let's go back and see how it's Broadway. Yeah, the constant. A and B are constant.
Oh, B is a constant.
Yeah.
And you should get around 286K when you're done with it. Is that what you guys got? Didn't get the thing, maybe this isn't quite right. Let's see.
yeah. Oh, I may have.
Yeah, that's right. Well, I'm telling you, I see a lot of people who are typing in their calculators. Make sure you do the powers of 10 before you stick it in your calculator. If you mess, it's so easy to mess up punching in with the powers of 10. Yep. Yes. Oh, yeah. Now, remember, what do you have to do with intensity? Doesn't it have a micron in it? Make sure you convert that micron into meters.
This is
So how are we doing on this? Is it coming out right yet?
The intensity would be 7 times 10 to the 6th, right? That's per micron, so per negative 10 to the negative 6.
Yeah.
Per micron, well, per micron is 10 to the minus 6 meters, 10 to the 6.
10 to the 6.
10 to the 6. Now you had negative 6, that was
Yeah.
It's over
I
negative
got
6,
it.
so it's
Okay.
times positive.
okay. Yeah, I should have caught that. So if you do that, it will come out.
Yeah.
Do you need me to drag you through this? Does anybody need to see it? Okay. One thing to remember is that I is going to be equal to 7 meters squared per micron is going to be equal to 7 times 10 to the 6 watts per amp, going to end up being meter cubes. And then lambda is equal to 10 microns is equal to 10 to the minus 5 meters.
Yes.
So you have to make one of those conversions in order to come out. Okay. So looking at how hard you're really working, I think I'm looking at a room full of people who are going to go and write their MATLAB functions to do this work from now on out, right? It's a pain. By the way, have you gotten the functions yet in MATLAB? We talked about writing your own functions.
not yet.
It will come,
Yeah.
okay? Because you definitely want to be doing that. I want to write one function for this and one function for that. We go this way. You don't want to be doing any more of this. Yes? Okay. Yeah. Okay, I think we can move on. So, that was just calculating brightness temperatures. It is something that you're going to see over and over again. It's going to become very common. But what is normally happening is a little bit more complicated. We were using a 10 micron sample because it turns out that in around 10 microns, there's no absorption by water vapor. There's a little bit of scattering by the atmosphere, not much. So it's called a window channel, which means if you're looking at something, if you're looking at the surface in a 10 micron wavelength, you're mainly seeing light just coming from the surface with a few smaller effects being added in. However, that isn't always going to happen. Sometimes you're going to have a wavelength which is going to be absorbed by the atmosphere. And if it becomes absorbed, of course you're going to re-emit, which means you have absorption and emission going on all the time. And we have to figure out how are we going to deal with that. So I'm really just going to show you how this is done. And we're going to end up with something which kind of intuitively makes sense. We're not going to make you do a whole bunch of calculations, but we want you to get the idea of what's going on. So, we can ignore atmospheric scattering. Why can we ignore atmospheric scattering at 10 microns? I'm talking about pure atmosphere, pure nitrogen and oxygen and stuff like that. 10 microns, what the size of a molecule? About angstrom, a few angstroms. It's so different that the Rayleigh scattering basically goes down to zero. Woohoo, we get to ignore scattering, so long as there's no nasty clouds or aerosols. Okay? However, we can't ignore absorption. And why can't we ignore absorption? We're talking about thermal things. Thermal comes from emission. If you have emission, what else do you have to have? Absorption. They're two sides of the same coin. So we can't ignore absorption. So our equation, here's the beginning of the equation. We have our intensity there. I really should put an emissivity there, but for some reason I didn't. So it becomes this equation right there. So we have our emission, and our optical depth will include absorption in it. Because remember, there's that absorption coefficient in the optical depth. That doesn't look like such a bad equation until you remember what that function looks like. Then you know it's really kind of nasty. Okay? But we're going to attempt to integrate it anyway because we're just kind of stupid like that. Okay? So we're going to throw in an integrating factor. Just e to the tau over mu there. And once we do that, we kind of get a little bit of integration by parts type of thing. So if you throw that integrating factor, this thing is a derivative of I e to the tau over mu. Okay? So, we're going to take that and we're going to run with it. This is the equation that we're going to end up with, where we're integrating by parts. And what we're doing is we're going to be integrating from the bottom of the atmosphere to the top of the atmosphere. So we're going to say at the bottom of the atmosphere, the optical depth is 0. At the top of the atmosphere, we have the total optical depth of the atmosphere. Okay? So, one thing that we do is, and I skipped a step here, so I probably have to write out the step for you. I think I skipped the step mainly because I was running out of space. But this little thing here, evaluated as 0 and tau f, that's going to become I e to the tau final over mu minus, and I should write this is the final and this is the initial, and then e to the 0. What e to the 0? 1. Okay, so that just becomes 1. And that's going to be equal to what I have on the other side here. So integral of 0 to tau b tau wavelength d tau e to the tau per mu. Okay. Next thing that we do is I say, let's go ahead and divide both sides by my tau there, by e to the tau over mu. So when I do that, I'm going to get e final minus e to the minus tau over mu. Inside the integral sign, I'm integrating over tau. But here I'm dividing by tau final. The tau final is a constant, so I can bring it inside the integral sign. 0 to tau b of t mu e to the tau minus tau final. Okay? And then I just move this to the other side, I'm over here. Okay? So, if you're not following that, it's okay. What that's happening is I'm doing integration. Okay? So do some integration, and I'm going to say that I0 is equal to emissivity times the black body. So I'm going to end up with this equation down here. And you're looking at that equation, and you're saying, I don't want to look at that equation. It has integrals, it has stuff like this, but it's okay. If we're going to look at each term and see if it makes sense. Because it turns out, if your physical reasoning is good enough, we don't even have to integrate. We can come up with this just by pure putting things together. For example, I already said that this is emission coming from the surface. It's the emissivity times the black body radiation, e to the minus tau final over. This is going through the atmosphere. What is this telling us is happening? Before I do that, let's make sure we have the stage set. We're up here at a satellite, we're looking down at the surface. This equation is what we're going to see from the satellite, looking down. Okay? So if we're looking, oh no. So, if we're looking at the surface from the satellite, we're going to see this amount of light is emitted from the surface. Then what happens? As it goes through the atmosphere, it's going to be reduced by Beer's law. So we got just the surface being reduced by the atmosphere due to Beer's law. So that term should make sense. So our panic attack in that term should be over by now. Okay? Emission just absorbed by Beer's law. Now we got this thing to worry about. This almost looks like that, except that we have tau minus tau final integrated over tau. So tau is being used as a variable, tau is increasing. If we're at the surface, tau is equal to 0. Okay, so that'll just be minus t final, just like that thing there. But as we keep going through the atmosphere, this is telling us we're looking at less optical depth. It's doing the same thing as that, except that it's looking at different levels in the atmosphere. So we're going to have our beam from the surface. Then we're going to go up a little higher. We have a new temperature in the atmosphere. We have new densities and optical depths, but we also have less optical depth that we're going through. Then we go through less optical depth. We're going to add that in. We go through less optical depth. We add all of those things together. It's the emission from the atmosphere. Okay? I saw a question back here.
I was wondering, what is mu?
Cosine theta.
Oh.
Okay, the cosine theta. Sorry. Should have reminded me of that.
So you mean every time that you have a change of temperature, you have to consider the tau?
Yes. Well, the optical depth at different places in the atmosphere are going to change. So this is differential optical depth. This is the amount of stuff at that layer. Then we go to another layer and another layer. Every time we go to a new layer, we're emitting more infrared radiation, and then being absorbed by the remaining atmosphere.
For example, we can just get that like tau minus phi 1 can be like maybe a variable A, which is
Yes.
every time.
Yes, we have less atmosphere that's absorbing. So we emit at whatever temperature we're at, and then it becomes absorbed by the rest of the atmosphere. And we're just adding all of that up. That's why we have the interval. Okay? So, it's kind of good for you if you could look at that equation and see if you can make every term make sense to you in your head. I'm not going to make you do any calculations with it, but just get the physical picture. If you can get that physical picture, you really do know what's going on. Okay? Is there a question over here? No. Okay. So, I'm going to break it down to simpler situations here to look at. Because the only thing you have to remember is you have something absorbed, you have something emitted, and that emission is also being absorbed at different levels and so on. Oh, there's the last one. Okay. So, we have transmission and absorption of light. So, this is, the higher it is, the more it becomes transmitted. So you see over here at 10 microns, we have almost perfect transmission through the atmosphere. Maybe a little bit of absorption. But where do we have most of the absorption? Right around in here. This is the near infrared. And they have a water vapor in there. A lot of the absorption is going on due to water vapor. But that's in the near infrared, maybe not as much emission there. And you know, over here we have oxygen is absorbing a lot in the infrared and so on. So it turns out that a lot of these lines do have to do with water vapor. And that has a lot to do with greenhouse. There's our methane. CO2 a little bit also kind of in the near infrared. Oh, actually this is not near infrared. This is more like the water vapor. This is what's called the water vapor band. Sorry, I was looking at these things, not at the wavelengths. This is the water vapor band, like from about 5 up to about 7 or 8 microns. Water is absorbed. Carbon dioxide is doing a lot more of the absorption downward between like 4 and 5 microns. But water vapor actually absorbs a lot more than carbon dioxide. And I think we had discussions before. So why do we talk about CO2 instead of water vapor when we talk about global warming? Water vapor is absorbing a lot more. Why don't we worry about that? Yeah.
Because melting ice.
Yeah, melting ice, but that's not directly where the water vapor. Where is the water vapor coming from? Everywhere, just about, ocean and everywhere. Do we have any control over that? We have no control over the water vapor. We do have control over the CO2. So even though it makes a smaller effect, it's something we can control. We can't control the water vapor. However, as we get more CO2 and more warming, what happens to the water vapor? We get more water vapor. So the CO2 causes more water vapor, which is where most of the global warming comes from. So we're just concerned about what we can control. Now if we look at emissivity, we see most things, these are like snow and silting, vegetation, most things have pretty high emissivity above 90%. A few times you're going to see like snow drops down, there's the granite, the stone that has pretty low emissivity sometimes. But most things we assume have pretty high emissivity. Yeah.
Could you like share this with us like online, because it's just so hard to like discern between like the colors.
Yeah, I mean, there is a version that we're trying to pull out. I can probably put together a webpage that has a link for it. Okay? So, given that most things have emissivity above 90%, the very common assumption that everything has an emissivity about like 0.95. So, we had a lot more of these, and now they're gone. Yeah, pass these, like one for every table. Going for your table. Oh, you're good. Table is right up at the front. Okay. So, if you point this at the wall or something, what do you see? You see a laser, but always look at the screen at the back.
76.5.
You're seeing temperatures. Now you can change between centigrade and Fahrenheit, you can see that. How do you think it gets the temperature?
The reflection. The transmission that it's getting
From the laser?
Yeah.
Okay, tell you what, there's a little button in there that has like a little circle in it. Push the little button and see if you still get the laser beam.
Oh, okay.
Okay? Now, you don't get the laser beam anymore. Do you still get temperature?
Yes.
Yes. Is the laser measuring temperature?
No.
No. Why do you think I gave this to you? Well, how do you think it measures temperature? Infrared. Okay?
So we can't see it.
The laser beam is just for pointing. Okay? It's not measuring anything. Now, I found in this day and age, oh, you guys don't have one?
We're not getting the laser beam from the.
Yeah, it's so much right.
The laser beam does nothing.
We're not seeing it anyway.
What?
It's not coming out.
You're not seeing any temperature?
Any laser, the beam.
Oh, well, there's a button you can push to get the laser.
We're pushing this one.
Pass it up to me. Okay, who likes to give it to you?
Yeah.
Your ours is 84 degrees.
Okay, so this thing is measuring temperature from infrared. Let's talk about that a little bit. What do you need to measure in order to get temperature from infrared? What information do you need? You guys just did it. What do you need?
Intensity.
You need intensity. So measuring intensity, what else do you need?
B. That's a
You need these constants.
Emissivity.
Emissivity. Do you think this thing can measure emissivity? No. It is assuming emissivity. It's assuming an emissivity of 0.95. Which means that if you shine at some things, the temperature would not be correct because the emissivity would be different. It's a retrieval, not a measurement. By the way, it's kind of directional, right? If you point it at the wall and you point it at somebody nearby, do you get the same temperature? Try it. Point it at your neighbor.
Yeah, it's temperature's high.
What happens to the temperature if you point at a person nearby?
It goes up.
It goes up. Okay, so the direction doesn't matter. How can you pick out direction? Look at your instrument. How is it getting direction? You can look into the mouth of the gun. Okay. How are you getting direction? You have a tube, don't you? It's being collimated. Remember we had talked about collimation. You actually have a collimated measurement. Now collimation works great with visible light, but now we're looking at infrared. So here's a question for you. When the detector there at the bottom is measuring, is it only seeing what's coming from outside the tube? Is that only IR coming from outside the tube? Where else could IR be coming from that the detector would see? Does the tube have a temperature? Yes. Is the tube emitting infrared radiation? Yes. So what does it have to do? It has to know what the temperature is of the tube and correct for that infrared radiation. So it knows how much this happened. If you want a fluid this big, stick it in the refrigerator for an hour, take it out and go out and start measuring things. What do you think will happen to the temperatures that you see? It will be lower because it's assuming that the tube temperature is going to be, so you can confuse it there. Now that, of course, it's measuring the tube temperature, so the question is, where is it measuring? Is it the same as the temperature that's receiving IR from stuff like that? Okay. So, interesting little device here. You will be using these tomorrow. So, let's do a little bit of thinking here. So we have water vapor here. We have a surface. The surface is down here at 295 K. We have layers of water vapor above it in the atmosphere. Eventually the water vapor goes almost to zero. Now the water vapor has a very strong absorption of 6 microns, moderate absorption of 4.7, almost no absorption at 10.3 microns. So you see it's water vapor. So if we have a device that's measuring intensity at 6 microns looking down, what temperature do you think it's going to see? We're at 6 microns. So it's very strong absorption. Is it going to seep down to the surface? No, the water vapor is absorbing. Okay? So we're going to see closer to the top. Okay? Think of it as looking through like pieces of tracing paper or something. If it's not very good tracing paper and kind of dark, you're only going to see the top layers. You're not going to see deeper in. Now we're at 4.7 microns. We're going to see moderate absorption. About what temperature might we see then? About 275. We're going to see part way in. Now remember, what's happening is light from the bottom, infrared from the bottom, is becoming absorbed as it comes up. Everything is emitting, but you're going to see kind of more emission coming from here with a little bit of absorption. So you're seeing partway in. How about if I have 10.3 microns, no water absorption at all? What would I see then? You'd see the surface would be emitting. Would the water vapor be emitting? Let's go back. Would the water vapor be emitting anything? No absorption. How much emission do we have? Zero. If there's no absorption, there's no emission. The water vapor doesn't exist at 10.3 microns. You're going to only see the surface. So all of these other things, like at 4x7, moderate, it's like the water vapor halfway exists. You're going to see halfway up the water vapor and so on. Okay? And if they're very strongly absorbing, everything from below is going to be absorbed. You're only going to see that emission coming from the very top, where nothing more is going to be absorbed. So you can see the temperature from the top.
It was at 285.
Yeah. Well, you probably more see like more 265, because it's very strongly absorbed. That makes sense?
And 4.7 was 275.
Yeah. 4.7 would be about 275. It's moderately absorbed. So from here, this stuff from 275 would pretty much, a lot will get out. We're going to have a mix of this and a mix of that. It's going to average to about 275.
And when you are in the bottom, there is more, less absorption, but more emission.
When you say at the bottom,
Here.
it depends on which wavelength we're talking about. If we're at the 10.3 micron wavelength, it's not going to notice the water vapor at all. That will be emitting because there's other things that will emit.
micron.
Yeah, the 10.3 microns is not absorbed by water, so it's not emitted by water. So it's as though all of this water vapor doesn't exist. You're only going to see what's being emitted from the surface.
You're gonna see what is emitted, or you're gonna, there is emission and then absorption. When it's down at the bottom, there is still absorption because in the water part, water area.
Okay, at 10.3 microns, the water vapor doesn't absorb or emit. Maybe a tiny bit, but not much of it. Okay? So what's coming from the surface would be from the ground, not from water, just from the trees and the buildings, stuff like that.
Which is the emissivity, not the absorption.
Well, emissivity and absorption are going to be the same thing.
Yeah. I wanted to know, when it's at that point, is there any more emissivity or more absorption? Less absorption or more emissivity? That's what I'm understanding.
Okay, at the surface, let's say the surface is just made of soil, no water. Okay, so the soil is emitting and absorbing. But we're only seeing that emission. We're only looking at what's being emitted from that surface. Okay? And then as it goes through the water, nothing happens to it because it's not an absorbent element.
It's not absorbing.
At 10.3 microns, the water does not absorb. So it just goes straight through the water.
Because of the size of the region.
Not the size of the wave, it's an electronic transition. It's actually rotation. So the water absorbs across a whole bunch of wavelengths because it can vibrate, it can rotate, it has different modes of vibration. All of these things will absorb energy. But it's not because of scattering, it's because of absorption of energy. So I know it's a little bit confusing. Now we're only talking about absorption, not scattering.
So the fact that it absorbs more allows for like a lower temperature to be observed or higher temperature? The brightness.
Are we talking about the surface or are we talking about the layers of the atmosphere?
The surface.
Okay, the surface is going to be emitting. It doesn't care about the water, it's just going to be emitting there. What matters is whether the atmosphere absorbs and then re-emits at the new temperature. So at 10.3 microns, we have emission from the surface, but the water vapor doesn't do anything to it, it just goes straight through.
Because of the size?
Not because of the size.
Oh,
Well, okay, there's no scattering. Scattering's out of the picture.
okay.
Well, we care when we're talking about absorption, don't get absorption mixed up with scattering. Because if you say because of the size, you're going to think, oh, the different wavelengths would be absorbing differently because of the size. No. Nothing to do with size if we're talking about absorption. Absorption all has to do with electrons either changing positions inside, molecule, or molecules vibrating or molecules rotating.
Okay.
So I also has to do with the fact that water is a polar molecule, so it has all of these different ways of absorbing the light. So it's not scattering, it's not size dependent. It's rotation, vibrational, and all of those things.
So the water doesn't have a capability to absorb the light.
At 10.3 microns, it does.
Okay.
At 5.6 microns and 4.7 microns, it does. At 6 microns, it will absorb very well. Okay?
And that's what yields the high temperature. Or is it the opposite? Is it the fact that at 10.3 it goes straight?
At 10.3, you're only seeing surface temperature.
So you would
So
have,
you're going to see lots of emission, no absorption, you're going to see the full emission. As you go to more absorption, some of that light will be emitted, will be absorbed as it goes through, but it will be re-emitted by the water as well, but being re-emitted at a lower temperature, so you get less radiance coming through. At 6 microns, everything from the surface is really going to be absorbed. All that you're going to see is what is emitted from the higher part where it's much colder, and then there's no absorption because there's no water above. Okay? Does that make any sense? Oh, wait a second. Okay.
So at 10.3 microns, there's emission going up to, let's say, the water level. There's no absorption.
There's no absorption by the
So
light.
you only see the emission at that temperature.
You're seeing what's being, think of the surface as being a bright light. And then you either have no fog above it, it'd be non-absorbent, or no smoke layer above it. As you get more absorbing, you're getting like thicker layers of smoke above it, that's absorbing the light coming up. But it's a little different that the smoke can glow as well. So if the smoke can absorb, it can also emit, but it's going to be emitting at colder temperature because you're seeing only the top of the smoke layer. You can't see through the smoke layer. You're only seeing the top of the smoke layer, which is also emitting light.
So, like, an analogy to that would be like, on like a really like cloudy day, the sun's like immense rays are dulled, so it doesn't feel like you don't feel the radiant.
Yeah, kind of going in reverse.
It's the reverse, but it's like the same.
Yeah, but the thing we have to remember is it's not just absorbing, it's also emitting. So you have to think of it as this glowing smoke which will absorb light, but then also re-emit light.
But at a
But the amount
lower
of emission
intensity.
depends on the temperature.
But the emission is at a lower intensity because
Yeah.
it's absorbed.
Yeah.
So much of it.
And the amount of smoke you see depends on the wavelength. So if we're at 6 microns, it's like we're seeing a very thick plume of smoke. We're not seeing any light coming from the surface. But the top of the smoke is still glowing, just not glowing as much as the surface. At a lower temperature, it doesn't glow as much.
Are we looking at this, let's say above the surface, above the atmosphere, looking down?
We're looking down from the satellite. Okay, so we're looking down from the satellite. You know what? Looking at this, I have realized I really need to put a satellite up here so you can see that we're looking at light coming at the satellite. That may be what's confusing people. Yeah. Well, I think this next one, I still don't have a satellite. So we have a satellite up here that's looking down at the surface but looking through clouds. So it can be looking through both these clouds are 260K. One cloud has an optical depth of about 0.5, another cloud has a very high optical depth, like 10 or 20 or something like that. So the question is, what temperature would I see if I'm looking through this cloud versus what temperature would I see if I'm looking through that cloud? So let's start with the thick cloud first. I have a satellite, I'm trying to look through this cloud, it's very thick. Do I see anything coming from the surface? No. What do I see? I see a cloud at 260 Kelvin. So I'm going to see an intensity that tells me, oh, I'm looking at something at 260 Kelvin. You guys okay with that? Okay. Now we come to a thin cloud. Optical depth of 0.5. About how much of the light from the surface comes through that? About half. You know, do an exponent to get it precise, but we can estimate and say about half. So half the light from the surface comes through. Do we get any emission from the cloud coming? Yeah. But would it be as much emitted from this cloud as from that cloud? No. That cloud is thick, you get full emission. This cloud is thin, optical depth of about 0.5. About how much of it do you think emits from here compared to that?
130.
Well, if you're doing it carefully, more like closer to 1/2. E to the minus 0.5. It's going to be close to about 0.5, more like 40% or something. But let's say about half. This cloud would be emitting about half of its potential light at a temperature of 260. Meanwhile, half of the surface light comes through. So what temperature do you think we'd see looking at that cloud?
157.
300, 260. we see half of this emission, we see half of this emission.
Wait, didn't you say that you do like 260 times e to the negative 0.5?
No.
Oh, okay.
The temperature.
So it's you can see twice.
You got tau mixed up with T.
Yeah.
It's about 280. You're going to see a temperature at about halfway between these two temperatures. This cloud is blocking about half of this, and it's emitting about half of this. So you take an average.
So you look at the emissivity,
Yeah.
right? And then you say, okay, so based on that cloud is spinning, the emissivity is 0.5.
Yeah.
So it's the temperature of the surface is coming up, and we see about half of that.
Yeah.
As well as half of the
Yes.
temperature. And then that one, let's say
Now they have an emissivity of about 1.
or 1.
1.
Oh yeah, so
The thing emissivity about 1.
it's only seeing the temperature.
It's only see the temperature of this cloud, nothing's going to be coming through. Okay? So those are the stretch, not, okay.
So you see about 140 because you said the average of the two.
Average of 300 and 260 last time I checked was not 140.
No, I thought you said you were
280.
seeing half of the surface temperature.
No,
In between.
you see half of the intensity from the surface temperature.
Oh, half the intensity.
Okay? So you're taking half of this intensity and half of this intensity. This is an intensity corresponding to a temperature of 300. This is an intensity corresponding to 260. You're going to get an intensity corresponding to halfway in between. Okay? So yeah, don't average temperatures yet. You have to average intensities, not temperatures. Into the microwave, it turns out we can average temperatures. We're not there yet. So tomorrow, you're going to be doing something that kind of mimics that. You're going to have one of these guns here. You're going to have a bath of either hot or cold water. And you're going to have saran wrap in between. So you're going to see that that's going to be coming up here. What do you think the saran wrap's going to do? And this is infrared, not visible. Saran wrap is clear in the visible. Do you think it's clear in the infrared? Not necessarily. So the saran wrap may be absorbing some infrared, but it absorbs, what else does it do? It emits. So you're going to get a mixture of these temperatures here. You're going to have to see if you can figure out what temperatures you're going to see. Okay? And by the way, if we go back to the clouds here, we said tau is equal to 0.5. That means that the transmission is equal to e to the minus tau. So if that's how much is being transmitted, how much is being absorbed? That much gets transmitted, how much gets absorbed? 1 minus that. Okay? Yeah.
So that's what you meant by initially we were talking about equilibrium
Yeah.
of transmission and emission.
Equilibrium is just used to establish the idea that the coefficients had to be the same. Once you're away from equilibrium, absorption and emission are not the same. But the coefficients stay the same. But because the temperatures are different, the absorption and emission are different. Okay. So when you do this tomorrow, think of the saran wrap as either a cloud or a layer of water vapor, stuff like that. You're trying to figure out how atmospheric things will interfere with your measurement process. Or maybe not interfere. You can also easily figure out how much of this stuff is in the way. Okay? Okay. So to give you an idea of all of this, we have 3 different wavelengths. We have visible. We have infrared in a window channel, which is like the 10.3 microns. And then we have a water vapor absorption. So we can see the clouds here. By the way, where do you think most of the energy is? visible, near infrared, water vapor absorption. Visible. Because it's visible, you can get higher resolution. Okay? If we have higher resolution, we get lower resolution here. We still see the clouds in both of these. The clouds begin to disappear in the water vapor. There's two reasons for that. One is lower resolution, but there's another reason that we just talked about.
The absorption.
Absorption by the water vapor. This water vapor actually extends above the clouds. So it's like we're seeing this layer above the clouds. So we see some of the clouds coming through that layer. Okay? So yeah, water vapor, you are seeing clouds, but you're also seeing the top of the water vapor above the clouds. Okay? Now, okay, we just talked about that. I'm going to move on. Microwaves. Microwaves are 20 to 100 gigahertz. People who do are typically electrical engineers, they prefer frequencies to wavelengths. So we're going to be converting it into wavelengths here. And the microwave spectrum is way out here. So we're talking about thermal infrared, but very low intensity. So it's going to be very low resolution. So microwave pixels are typically like 20 to 40 kilometers. So why would we care about microwave source of radiation? It's mainly going to be from the surface. Does the atmosphere scattering the microwave? We're like about centimeters or so. Not really. Okay. So the source of radiation is going to be typically their surface. Cloud droplets are so small that they don't scatter microwaves either. They don't absorb much. So you really don't see much coming from the clouds in the microwaves. So they're pretty much transparent unless they have ice or large drops in them. Soil penetration is just going to go in a little bit in the soil. And what can we see with that then? Well, we can see the water content in the soil. We can see the big drops of ice particles in the clouds. So we use microwaves you normally see through the clouds to see the surface or to see bigger stuff in the clouds. And the nice thing about microwaves, if you take this Planck function, the frequency is becoming much smaller. We can simplify it, and you end up getting to the brightness temperature. The intensity is proportional to the temperature itself. So when you're working with microwaves, people often talk about brightness temperatures more than they talk about intensity, because the two of them are proportional to each other. Okay? We're going to be talking about, we're running out of time, we're going to be talking about this again tomorrow. So I'm going to skip through all of this stuff. Save it for tomorrow. And get to our homework. So, satellite is measuring irradiance, and we're talking about the 10 micron window channel. I'm giving you emissivity. I want you to calculate the temperature, or I should say the brightness temperature. We're going to use the same emissivity across the entire spectrum. So I want you to figure out how much energy is being radiated and what wavelength would the peak emission be. So all of this is stuff we've already kind of done. There's no tricks here.
So like the 10 microns, we're looking back at that like 6.7, 4.3, 10 to get an idea of the absorption.
Yeah, but this is a non-absorbing, non-water vapor absorbing.
Oh, this is
Yeah. So we're going to say there's no water vapor absorption. We're going to just do a nice, clean brightness temperature calculation. Okay? Be easy. And tomorrow we'll put everything together to find out how we actually use satellite data to get information. We haven't really done that yet.
the scatter plus absorption.
Scattering and absorption, we're going to see a little bit of everything.
The combination of those.
We try to avoid that, but sometimes it happens.